Okay, so happy Wednesday. Welcome back. Everybody have power? Yeah, I've heard a lot of Vermont is still dark. Okay, so today is our very last day of new material for the semester. On Monday coming up, it's our review day for test number 3, which is Wednesday, 1 week from today. 1 week from today is our exam. Also today, finance project is due, so if you've got it, great, throw it in the folders for me. If you don't have it, there are lateness penalties that accrue every day that it's late, so get it into me as soon as you can. Any questions on the calendar? Okay, so then one quick thing, not about our calendar, but raise your hand if you've already registered for the spring. Wonderful. So there are a few folks that have not yet registered for the spring, and so I say this to you. In the last few days before each semester, there is a mad rush for people trying to take classes and then learning that everybody's trying to take the same classes that they are, and lots of courses are full. So to avoid the stress of trying to create your ideal schedule when lots of things are filled, I'd encourage you to register sooner rather than later. That last week right before a semester starts is the worst time to be registering. So if you have a few minutes today, go find your academic advisor. If you don't know who that is, ask me after class and I will tell you. Your advisor probably isn't going to be available very much during the break, but the Academic Advising Center is available all break and they can help you get registered. So get registered instead of waiting until the last minute. All right, so here we are on page 35. We'll start all the way up at the top. And let's go to Sam for our next.
Our next fractal is called start with any fractal. It does not necessarily have to be lateral and remove the middle intermediation.
Okay, so take a look at this first picture here. We've got our original triangle called a seed, just like for the Koch snowflake. The first triangle was a seed. But now instead of adding things like we added triangles to make the Koch snowflake, we're going to subtract triangles. And we're going to subtract the, quote, middle triangle. Now that's not really well defined. So I'll say what you do is you go to the midpoint here. And then you go to the midpoint over there. I'll call that one N. And then you go to the midpoint of the last side. I'll call that O. And you connect the dots of those 3 midpoints. And that's the thing that we take out. Buy it? So you go to the 3 midpoints, connect the dots, remove that triangle, which is why it's now in white over here on step 1. But we can also look at step 1 as being 3 separate triangles. And for each of those triangles, for example, this top one, I could go to the midpoint on each side and remove that triangle. And that's what's happened over here. Will we run out of spaces to remove? Louder for us, Suanne. Yeah, there's even if there's more and more white space as you go on, right? You can see that there's we can see there's more and more white space as the shapes go to the right. But there's always stuff there, right? Even if we don't have enough pixels to represent it, there's always going to be teeny tiny triangles there, more and more of them, in fact. And so, yeah, we can keep doing this forever. And then we're going to analyze some specific results about the forever Sierpinski gasket. Let's go to Ashley after. Okay, so there it is after step 7, and there's still plenty of stuff to take out. Lots of little triangles there that you can cut things out of. All right, let's go back to Brendan for like. Okay, so moving on to number 1, it turns out that the self-similarity we saw for the Koch snowflake, you guys remember the banjo video? Yes. Right, so that self-similarity where you keep zooming in and it keeps looking the same, it appears here as well, and that self-similarity is exact, universal, and infinite. Exact means it's perfectly exactly the same, as opposed to lightning, which kind of looks the same, but it's not exactly the same as you zoom in. Universal, meaning you can zoom in anywhere you want. and infinite, meaning you can keep zooming in forever, like in that banjo video, and it will just keep looking the same. And so, for example, if we focus in on this this blue triangle over here and expand it to that thing, what does it look like? It looks exactly the same as the original one, right? And if we instead focus our attention on just this tiny, tiny blue triangle over here and expand it, it looks just like the original one. And so you can pick any old triangle you want, like that guy in there, and expand it, and it will just be another full infinite copy of this Sierpinski's gasket. Okay, let's go to number 2. Matt. Okay, in terms of perimeter, let me just, so it's fine for you to turn the page. I'm going to stay here for just a second. Perimeter of the original triangle, that's not what I meant. Perimeter of the original triangle is just that plus that plus that, right? But the perimeter of the new one, like it's got a hole in it, and we don't have a lot of practice taking perimeters of shapes with holes in them. So it's still there plus that. We buy it? Like that's what we mean by perimeter. It's like if you just have to, like you have to like put a little piece of string everywhere that is a boundary of this thing, even if the boundary isn't on the outside anymore, right? And so we can come to this next guy and you can see the perimeter is even bigger because it's all of that, and it's that, and it's all of that. So basically like every one of these triangles we cut out adds more perimeter, okay? All right, let's go to the next page. Okay, so we're going to assume that each side of the seed triangle, the original triangle, is a length of 1. And we want to know what the length of the boundary of this guy is. So if they're all 1s, then the length is 3. So far, so good. And now we're going to look at step 1. We'll call this P sub 1 for the length of this guy. So this one might not be as obvious, but let's see what we can do. So we said that this and this and this, they're all 1s. That's fine. But then we've got this new shape on the inside. Any guesses for how long each of those green segments is? Yeah, it turns out it's exactly a half. If you go to midpoints, of two sides, then the length of that guy is always half of the third side. So there's kind of this opposite type thing happening because the bottom is a 1, the top green one is also is a half of the 1. So a half there, and a half there, and a half there. So how much is it now? 4.5, we buy that? Right, because we had the 3 that we had plus another 1.5. Okay, how about in blue, the lengths of these guys here? These are all the quarters. They're half of the half. So that one there is a quarter. Yeah, so then the whole triangle there is 0.75. Well, how many blue sides do we have? Like if we look at all the triangles that are the same size. Yeah, how many blue sides are there? There are 9 of them, right? So 9/4 is the total of the new stuff. All right, so maybe going into decimals wasn't so great. So so another way to write this 3 is 3 plus 3/2. You guys remember lowest common denominator stuff? 6, 9. Can we do that? Do we know how to do that? Nod your head. Tell me you know how to do that.
Yeah.
Both, either one, right? Okay, and so then here, we had the 3 and the 3/2. That's what it was before. And now we're adding, how many we said? It was 9, and they were each a fourth, right? So 9/4. Okay, so common denominator here is a 4, 18, 9. I get this. It'd be super if somebody could confirm or deny. Confirmed? Okay. Okay. All right, and now I don't feel like counting anymore. I'm just gonna draw one. Yeah, can we figure this out like without actually like counting everything? So yeah, like there's a formula here somewhere. So yeah, so how many of these little red triangles are there? 9 of those guys, right? And every triangle has 3 sides. So how many red sides are there? 27, we buy that. So we're going to take whatever we had before and we're going to add 27. And then how long is a single red side? Is now an eighth, half of the quarter that we had before. So 27 eighths. All right, I'm lazy. It's this thing over here plus 27 eighths, right? Okay, so there's definitely patterns lurking underneath here. Okay, so the question is, can we figure out a way to write a formula here for the length of the boundary at step n? All right, let's just take a step back and stare at I don't want to say this. I'm going to go to decimal land for a second. This one is 4.5. What was the next one? 27 fourths is 6.75. And then one more plus the 27 eighths, 10.125. Okay, we're going to look at that, just that list of numbers, the decimals. So 3 goes to 4.5, goes to 6.75, goes to 10.125. So remember way back when, an arithmetic sequence is where you keep adding the same number. So with a moment's reflection, we can decide whether or not this is arithmetic. Are we consistently adding the same number? No, right? The first one we're adding 1.5, and the second one it's what, 2.25? It's not consistent there. A geometric sequence is where you multiply by the same number. Here, it's much harder for me to look at that and know if I'm multiplying by the same number, but I could use my calculator to help me. What would I do to figure out what the ratio was if it was a common ratio? Divide the 4.5 divided by 3, right? So that one I can do in my head. That's 1.5. But then we get to the harder stuff. 6.75 divided by 4.5. Okay, that one I can't do in my head. What is it? 1.5. And if we do 10.125 divided by 6.75, it is 1.5. And so we didn't really realize it, at least I didn't realize, but it's a constant ratio. We keep multiplying every time by 1.5. And so if we keep multiplying by 1.5, let me flash up here old formula for you, this guy. So right down here was our formula where you keep multiplying by the same number. Can you guys write that thing but use the numbers that are relevant to this problem? What's the starting amount for us? 3, that was the original length, times the common ratio is 1.5, and then raised to the n, that's just part of the formula. So that's it. Okay, so what did we say it was? Yeah, great. So there's our formula. So what happens to the whole boundary as we go to infinity, if n goes to infinity? You keep multiplying something by 1.5, what happens to it? Bigger, bigger, bigger forever. So what does the boundary approach? Infinity, right? Okay, so that's fine. And then what about the area? Is the area getting bigger or smaller? If we just look at the colored stuff, not the white stuff anymore because the white stuff was taken out. So the area gets smaller because you keep removing things. So it's getting smaller, smaller, smaller. What's the kind of natural limit if we let things get smaller forever? Like maybe 0, but it's also possible it never gets to 0. Like maybe it just levels off at like 0.003 or something, you know, like some small number, but not quite 0. So let's see what we're doing here. At step 1, the question is, what fraction of the area of the seed triangle, that's the original filled in one, still remains? What fraction is still shaded in step 1? It's 3/4. We buy that, right? So we have 3/4 of the area that we had before. And then looking at step 2 compared to step 1, that's in part B here, what fraction of the area is there in step 2 compared to step 1? 9/12, which reduces to 3/4. Do you see it's still 3/4? I mean, Zeke actually counted it out for us, right? He said there's 1, 2, 3, 4, 5, 6, 7, 8, 9 that we still have out of a total of 12, counting the 3 smaller white spaces. So we still have 9/12 of what we had, which is exactly 3/4. But I think that makes sense because if you just look at this guy compared to what it used to be, what fraction do we have for just the top part? 3/4, and it's the same consistent pattern everywhere, right? So if everything is 3/4 of what it used to be, then the whole thing is 3/4 of what it used to be. So again, we have 3/4 of what we used to have. And do we buy it? I mean, like, it's going to be 3/4 again? Yes? Yep. Like, we focused on just that one and just that one, and so there's lots of 3/4 everywhere. So all told, it's a consistent 3/4 every time. So part D, looking for a recursive and explicit formula for area. Okay, so let's call it A sub n equals. When we're doing recursive, do you guys remember the basic pattern? It was always P sub n equals, yeah, like P sub n minus 1 would always be the first thing we would write, and then we would adjust it. So what this says, if you want to get the area, you look at the area one step before, and now we'll adjust it. What do you do to the area from one step before? You multiply it by 3/4. There's your recursive formula. Okay, so that's the recursive. Now we'll do the explicit. A sub n equals, so I'll write the formula in words up here that we had flashed up here a minute ago. So it was the start amount times the common ratio to the n. You don't need to write that. Ratio to the n. So for the explicit one, I'm telling you assume the area of the seed triangle is just 1. So 1 times common ratio. 3/4, right? That's what we do every time to get the next number raised to the n. Yeah, and then technically we should put that over here as the, we'll assume the seed is a 1. We need a starting number. Okay, so then what happens if you repeatedly multiply 3/4 by itself over and over again? What do we approach? 3/4 times 3/4. You can do it on your calculator. Start with 3/4, multiply it by 3/4, multiply that by 3/4. Just do a few of them. Yeah. Smaller and smaller towards what nice number? So who's giving us this theme music right now? So what do we approach long term? Yeah, closer and closer to what? 0. Yeah, we're like 3/4 times 3/4 times 3/4 keeps getting smaller, smaller, smaller. You have less and less and less. And in the long run, the perimeter, sorry, the area approaches 0. Okay, so in number 4, it's got the formulas that we saw. I guess we skipped one of them. We did the explicit for the perimeter, then the area down here, we did both the recursive and explicit. We didn't do this one, but hopefully it makes sense. For the perimeter, we just said you keep multiplying by 1.5, 1.5. And so that's what that recursive says. And so if we take it forever in part C, it says the perimeter is infinity, but the area is 0. Which is actually kind of a strange juxtaposition. We'll see how it's used down at the bottom here. Okay, so you can see the kind of triangular patterns, like this is some, what is this kind of shell called? Is it a conch shell? Maybe, yeah, maybe it's a small conch shell. Yeah, and so you can see kind of like Sierpinski-esque. Of course, it's not perfect, but you can see like big triangles and then smaller triangles, and that looks kind of like Sierpinski gasket. And then over here, I don't know if you guys can see, how well is this? Can you guys see that on your handout, or is it too? So what shape does that look like? Doesn't it look like Sierpinski's gasket? I mean, you can see like the darker spots is where there's nothing, and the antenna is taking up all the rest of it. So let's talk about why that's a really good thing in terms of an antenna. What can you say about the perimeter or the amount of wire that's used there, big or small? What happens to the perimeter when this thing goes forever? It gets big. What can you say about the area that it takes up? It's small. And so that makes it quite ideal because there's a lot of surface area for these like cable TV rays to come in and hit or whatever, but it takes up a very small amount of space in reality, right? And so this is a nice thing in terms of a design for an antenna. And then over here, what shape do these guys look like? Yeah, that's the Koch snowflake stuff that we saw the other day. Same idea, taking up a small amount of space, but a large surface area. Okay, so on the next page, number 7. Who's our reader now? Matt, did you read? Did you read, Matt? Jen. Go ahead. Okay, let's pause right there. So we're just going to pick a point, any place you want. Could be in, could be on, could be wherever. I'm just going to start right there. I'm gonna put a 0 there just so I can keep track because I'm going to have a lot of different points in a minute. So any point you want to start. We roll the die. It comes up 1, 2, 3, 4, or 5, or 6. All right, somebody shout out a number that just came up on your imaginary die. 4. So what that means is you take your current point and you go halfway to that top vertex. If you get a 4, you go halfway to B. So I'm going to go halfway to B and I'm going to put a new dot somewhere around there. I'll put a 1 next to it to let me know that's the next one in my list. Everybody see what we just did? Okay, somebody else shout out the imaginary die roll. 6. So 6 would say I go towards C, and I'm supposed to go halfway towards C. So halfway towards C, maybe there-ish. My 0 was kind of in the way of that dot. Okay, somebody else shout out a number. 2. And so then we go halfway towards A from the current dot. So maybe someplace over here. And we just keep rolling. Okay, so why do we do this? Well, you know, people didn't always have like the Wii, and so like they had to come up with stuff. And so what I want to show you is the surprise that happens here. So I'm going to pull this up here. Okay, so this is Java applet. You have the link. I think the link is there in your packet. And so all it's going to do is it's starting with an arbitrary point, and then it's just going to roll the die. And so I'll push start, and we're going to see new dots come up, and it leaves like the blue is the current one, and it leaves a little trail of small black dots. We see it? Can you guys see this in the back or no? Okay, and so you can see like which one it's getting close to, right? And halfway. So you can tell where it's going, right? And so we just get this collection of dots. Now you got to be really patient if you want to see the punchline here. So let me stop it. I don't have a lot of patience, so I'm gonna change the delay to something smaller. It still seems like it's. Why is it so slow? Continue. Stop. Start. I know, but like with the delay of nothing, it should. There we go. We could do it in with more of a delay. Or let's start over. Isn't that crazy? But isn't that crazy? Like it becomes the Sierpinski gasket. Like it's crazy. How? Right? How? How does that happen? Yeah. Okay. So so that is that. Oh, you can even mess with the like the kind of triangle. Let's see if that matters. Yeah. Yeah. Like it's just it's crazy. Yeah. Like it just tilts everybody, right? All right. So here's what we're gonna do. On the next page is this thing called Pascal's triangle. Anybody ever seen Pascal's triangle? So there are a bunch of questions that you're going to answer about Pascal's triangle on this page and the next. Raise the flag if you get stuck. What did we discover when we colored these evens and odds? The triangle thing. I think Sue Ann has a particularly nice colored in triangle. Can we hold that up? Everybody see that? And nice. Reds and greens. All right. So check this out. So my friend Niels, who teaches over at Deerfield Academy, he made this. So this, I'm going to, all right, so you're going to have to rotate your head, but this is Pascal's triangle looking at it this way. Do you guys see the 1, 1, 1, 1, 2, 1, 1, 3, 1? See it? Yes? Okay, and so in terms of coloring things in, we were looking to color in anything that was even. Anything evenly divisible by 2 got colored in one color, right? Yeah. Now you guys didn't actually do the division with the remainder of 0 and 1. Shh, in the back. So if you actually do the remainder, like if you take this guy and divide it by 2, what's the remainder? Is 0, because that number is divisible by 2, yeah? Okay, but if you take this guy and divide it by 2, what's the remainder? Is 1. The remainder is 1. The decimal is 0.5. But the remainder is 1 because after you pull out the 14, which is divisible by 2, there's still 1 left over. So what Niels did is he changed these guys to zeros and ones, whether they were even or odd, just based on their remainder when you divide by 2. So that's this list right here. So I'll go back up here, up to the top. So this is just all zeros and ones based on whether the number was even or odd, okay? All right, so I'm going to, no, but you guys know that with Excel, you can, like as soon as you got one formula typed in, just drag it, and it does everything. All right, so I'm just going to zoom out. Now, I don't want you guys to think there's like any kind of like technical, like I'm not doing any wizardry here. I'm just zooming out, and you tell me if you see something. Can you see it? Can you already see it? No, there's no coloring here. This is just flat zeros and ones.
Yeah, you can totally see it. You're a wizard.
Okay, so this last step is just because Excel can't quite, like it's just not enough pixels, and so it just zooms out, and there you go, Pascal's triangle. Now, so here's some more. So check this out. So this is now colored. Anything that's evenly divisible by 2 got colored in red in this case. Now, there's nothing special about divisibility by 2. We could also have looked at the numbers that were divisible by 3, right? And so you guys could look at your triangle right now and you could just, if you had like a blank copy, you could just color in the numbers that are divisible by 3. Yes? Okay, so that's this. So did you see it? I'll put it back. You guys were looking at this thing. And then if you divide by 3, it changes, but it still looks Sierpinski gasket-like. Okay, let's look at the numbers that are divisible by 4. That's those ones. Divisible by 5. It's like different kinds of similar patterns, right? Like here, there's many fewer triangles than there were here, right? There's a lot more triangles that I can kind of see, like smaller ones. Okay, so those are the 5s with this massive one in the middle. So there's this huge block of numbers that are all divisible by 5. You don't have enough data to like see this block, but if you had enough data, you just see this massive like 1,000 by 1,000 set of numbers that are all perfectly divisible by 5. So here are the ones divisible by 6, 7. There are the 8s, the 9s, 10s, 11s, 12s, 13s. Anybody seeing any kind of pattern here? Those are 14s, 15, 16, 17, 18, 19. 19 looks a lot like 17. Yeah? And let's just look for ones that look like, I just want to look for ones that look like that, okay? All right, so 16, 15, 14, 13. So 13 looks an awful lot like that, right? There's this big one over here. Is it every 3? So 13, 17, and 19 are all primes. So which one do you want me to go to next to see? Let's go to 11. Prime. All right, let's go past 19. What's the next number after 19 that we're? 23. All right, there's 20, 21, 22, 23. So it's like this weird, like there's all this order, like the ones that are divisible by prime numbers just form these like really orderly groups of triangles. What's next after 23? 29, right, let's say 24, 25, 26, 27, 28, 29. Like it's really predictable, but it's so surprising. Like even though I knew this was going to happen, like I'm still surprised. Like 31 seems the same. Yeah, but it's just, I don't know. It's just quite surprising to me, like that there's all this order in this simple list of triangles. All right, so the homework is in the usual place. This is the last homework assignment of the year. Enjoy it. And we're going to let you guys out a minute, 15 seconds early, so don't say I didn't ever do anything for you. And we'll see you on Monday. It's not too early to study those sample test problems that are a few pages away in the packet. See if you can find some time this weekend.